to face. And that's why we have to put a control on the ways we are nowadays utilizing the energy. The best thing to do it is to conserve energy or to minimize the energy consumption as far as possible. Now, if you see the energy which we are receiving from sun, which is known as the perennial source of energy, and even in renewable energy, sun is the perennial source of renewable energy. So you can see that we are receiving from sun around 10 raised to the power 22 British thermal unit. So if you are going to means convert it into joule, it is around say 1.005. So more or less it is equivalent to joule only. So but the thing is that although we are receiving 10 raised to the power 22 British thermal unit of energy from sun, but our world's annual energy consumption is quite less. But then also we are not able to cater to the requirement, even though we are receiving such a huge amount of energy from sun per year. And now what is the reason for it? Anyone wants to participate and say what is the reason why we can't use solar energy to its maximum possible level? Yes. Okay, so you know what? Solar energy is quite dilute, like it is not concentrated at one place. So we require some sort of technology to make it concentrated at one place, even if it is solar photovoltaic technology or even if it is solar thermal technology. Secondly, solar energy is not available throughout 24 hours. Like we are having the diurnal variation, accordingly, the variation of solar energy also takes place. As the earth rotates about its own axis and the day and night formation takes place, the solar energy is also not available with us for 24 hours. Again, the earth revolves around the sun because of the 365 days time which it takes to complete one revolution. So that time also the amount which we are receiving from one particular point on Earth's surface is not similar because of the seasonal variations. So you can see that day and night variations, seasonal variations, these are some of the factors which is to be kept in mind when we are saying that we are receiving 10 raised to the power 22 British thermal unit from solar energy. Is it clear? So that is the thing. But the thing is that if we want to utilize this solar energy to its maximum possible level without getting affected by this diurnal variation, without getting affected by this seasonal variation, then definitely we should have some mechanism to store it over a period of time. So today I will be speaking about efficient storage system, efficient solar thermal energy storage system, which can be coupled with various non-conventional type of cooling technologies. Now, I think you will understand what is conventional and non-conventional type of cooling technologies. The cooling technologies which are not utilizing any active power for compression of the fluid. For example, in vapor compressor, we require some sort of mechanical compressor. So if we don't require that, then it is known as non-conventional type of cooling technology. Of course, there are other non-conventional type of cooling technologies also, but this is the one which I want to highlight over here is the vapor absorption type of cooling technology. So this vapor absorption type of cooling technology is requiring a very huge amount of hot water system, which is to be perennially given over a period of 24 hours. But if we are using solar energy, then definitely we can't utilize it for 24 hours. Now we will be designing a kind of energy storage system so that we can give this perennial source of hot water to the vapor absorption cycle. And that is the whole study which we will be discussing today. Now, there are various disadvantages of this solar absorption chillers. One of the greatest disadvantage of this solar absorption chillers or solar absorption cooling system is its coefficient of performance. As compared to that of vapor compression cycle, the coefficient of performance of this solar absorption chiller is quite low. like you can say around 0 0.4, 0 0.5. But if some way or the other you can make it multi-staged with double effect and having a perennial source of hot water, then you can improvise on the coefficient of performance to around 1.4 in comparison to that of zero point 0.4 or zero point 0.5, as I mentioned. Now, this solar absorption chillers, they require a hot water of around 160 to 180 degrees centigrade. How to provide this hot water of 160 to 180 degrees centigrade over a period of 24 hours? And for that only, we will be requiring an effective energy storage system. Now, coming to the different types of energy storage system, there are latent heat energy storage system. If I'm speaking about the thermal energy storage system, there are latent heat thermal energy storage system. There are sensible heat thermal energy storage system. And if you are going in terms of the composition, then there can be thermochemical type of energy storage system, which works at a bit higher temperature. Then there can be phase change material, or the you can say organic and inorganic type of latent heat and thermal energy storage system. And then there can be some sort of inorganic salts, which can also be used as latent heat thermal energy storage system. So you will see that there are n number of classifications which we can do for this thermal energy storage system. But another important classification of this thermal energy storage system is on the basis of the temperature. Like we can have low range temperature, say up to 100 degrees centigrade. We can have medium range temperature, say from 200 to 350 degrees centigrade. And we can have high range temperature, which is from 500 degrees centigrade and beyond it. Is it clear? Yes? Okay, so I will go ahead. So this study today, which I will be showing over here, it is for medium temperature thermal energy, latent heat thermal energy storage system, which works in the range of say 140 to 160 degrees centigrade. Now you can see from this slide, let me just put the pointer on. So we are having a latent heat thermal energy storage system, which is being connected to this absorption chiller. This is the latent heat thermal energy storage system, and this is the absorption chiller. And this absorption chiller is giving a chilled water circuit to the building, which is to be maintained at a particular temperature, say 25 degrees centigrade. Now, when we are receiving energy from the sun, if we can some way or the other store in this thermal energy storage system, then this chilled water loop will be available irrespective of whether we are having sun or not. So that is the whole reason for which this medium temperature storage for solar cooling is quite important when we are trying to utilize the non-conventional type of cooling technology for cooling a control volume. Okay. Now, as I mentioned, that there are various types of phase change. There are various types of thermal energy storage system. So one is the latent heat type of thermal energy storage system. In latent heat type of thermal energy storage system, what happens, the phase of the material changes, and over a period of time, by virtue of the change of phase, without changing the temperature, it can store energy and it can release energy. Like when it is getting charged, then it will be releasing. Getting discharged, then it will be storing the energy. So why this PCM? This PCM, in comparison to that of any sensible energy storage system, requires a small space, and the energy density is also quite high. So that makes it a very tangible solution of thermal energy storage system in comparison to that of any sensible type of energy storage system. And that is the reason for which we go for a PCM based thermal energy storage system or a latent heat thermal energy storage system. Is it clear? Okay, so when we are speaking about any thermal energy storage system, there are two very important thermophysical properties which should be kept in mind. These two thermophysical properties are the thermal conductivity and the heat storage capacity. Now, if you know, Prandtl number is something which incorporates both of these properties, the thermal conductivity as well as the heat storage capacity. But when we are speaking about this latent heat storage system, which will be absorbing the heat and then it will be releasing it by virtue of the change of phase. As the material undergoes phase change, the thermal conductivity of this type of latent heat thermal energy storage system is very low, although it will be having a very high energy storage density, energy per unit volume, but its thermophysical property, the thermal conductivity is very poor. And one more thing is that it will be having a very good heat storage capacity. But to make an efficient latent heat energy storage system, we require both the thermal conductivity to be very high so that it can dissipate the heat, and at the same time it should able to store maximum amount of energy by virtue of its good heat storage capacity. We don't find this type of properties in any material which will be having a very good heat storage capacity and very good thermal conductivity. Therefore we have to go for some sort of arrangement, some physical intervention, making the geometrical changes by utilizing some sort of extended surface or fins, or we can use multiple phase change material, making a system with cascaded type of latent heat energy storage system, or we can encapsulate the phase change material, which can also enhance the thermal conductivity of the material. So this way, some way or the other, we can have this type of interventions so that we can get an improved thermal conductivity. One very relevant way of increasing the thermal conductivity of any phase change material is high conductive nanoparticles. These nanoparticles, they can be utilized, they can be mixed with the phase change material so that it can come as a means to increase the thermal conductivity of the phase change material, which already is having a very good heat storage capacity. So in this slide, I am showing various mechanisms through which we can enhance the heat dissipating capacity of any latent heat thermal energy storage system. Besides this, besides including nanoparticles, we can also include metal foam composites. We can have non-metal or graphite composites, or various other type of composites which can be honeycombed structured and impregnated with the phase change material to improve the thermal conductivity. So there are various ways through which you can enhance the thermal conductivity. I think it is hanged. Just just a second. Okay, so these are the various ways through which we can introduce we can introduce the concept of increasing the thermal conductivity in a particular phase change material, or we can introduce the heat dissipating capacity of that particular energy storage system by introducing some sort of physical intervention like utilizing extended surfaces or fins. So there are a lot of literatures which has been studied, or which has been carried out. Lot of studies has been carried out in this area. But after a proper literature review, we found that still there are some research gaps for this medium temperature, like 120 to 200 degrees centigrade. For us, it is around 140 to 160 degrees centigrade. Very few studies are reported for this medium temperature latent heat thermal energy storage system. And then if we are saying that very few studies are available, then even the employing of fins or intervention of the physical geometry of that particular system has also not been studied to find out whether there is any economical and effective way to improve the thermal performance of the latent heat energy storage system. And of course, if we are saying that, then definitely we should also look for optimized size of the fin so that it will not hamper the convective flow of the molten PCM. And then there are very few studies pertaining to nanoparticles which can enhance the overall thermal conductivity of the latent heat energy storage system, so that we will be having a proper dissipation of heat whenever it is required. There are very less studies to find out how the conduction and convection Hello. Yeah, there are various trade-offs which are to be carried out. Various trade-off studies are to be carried out to find out the effect of increased conduction due to nanodispersion and deterioration in the convection due to enhanced viscosity. Of course, there are various studies, but the insufficient information regarding the temperature dependence of the thermophysical property of the phase change material is also a criteria. Therefore, we developed an experimental system which can take care of this various limited study which is available for this medium temperature application of latent heat energy storage system. Now, the objective of this present study is to identify and characterize the most suitable type of phase change material which will be catering to the need of this 140 to 160 degree centigrade 160 degree centigrade temperature range. So we have to develop a storage model and validate it and see how in-house development of this storage model in this particular temperature range can be upscaled to that point where we can have it in the actual system where we are having the requirement of 140 to 160 degrees centigrade thermal energy storage system. Now we have to conduct the investigation of the thermal conductivity also to see how the introduction of graphene nanoplatelets will have an effect on the overall thermal conductivity of the system. Of course, the enhanced viscosity due to this GNP dispersion will also to be looked upon, has also to be studied to find out is there any effect on the natural convective heat transfer which may get intervened by this dispersion of the graphene nanoplatelets. Then we should also study the melting enhancement that we will be showing in our subsequent slide using a combination of both GNP and optimized fin in a phase change material based heat exchanger. So therefore, and also at the end, I will be showing you some studies which has been done to change the shape of this phase change material based thermal energy storage system from cylindrical to conical and find its effect. So as I told that thermal characterization, like the estimation of the specific heat of this phase change material is quite important. So what we did, we developed a criteria to test all the phase change material. Basically, we started with a binary eutectic of lithium nitrate and potassium chloride to do the testing to estimate the thermal behavior or the heat storage capacity of this particular eutectic in the range of temperature in which we have to function. And of course, this binary eutectic temperature is having a melting point in that particular range where we are estimating or where we are planning to design our energy storage system. Is it clear? Now, the difference in how this estimation of the heat storage capacity is done, it is done by introducing a differential scanning calorimeter or calorimetry system, which we are having in our lab. And how it works on the principle of difference in the amount of heat which is required to increase the temperature of the sample, and the reference is measured as a function of temperature. So both the sample and the reference dish are maintained nearly at the same temperature. So these are the results of the melting and the solidification for the lithium nitrate potassium chloride eutectic. We found that the melting onset takes place at 164 degrees centigrade and the peak happens at 168 degrees centigrade. Whereas when we are going for the solidification on the other way around, like say charging and discharging, then in that case, the temperatures are, just a second. The onset temperature is 159 degrees centigrade and the peak temperature is 157.6 degrees centigrade. Now, on the basis of that initial characterization of the lithium nitrate and potassium nitrate eutectic system, we again moved ahead to design a prototype of the experimental setup, which can be a precursor to the actual design of the latent heat energy storage system for the same range of temperature. So this slide pretty much shows the latent heat energy storage system experimental prototype. So you can see that we are having the PCM, which is being annulized with heat transfer fluid. Basically, hot air is being pumped, and this hot air is being generated with the help of a coiled electrical heater, which is providing hot air at a certain elevated temperature, which can be certain elevated temperature, which can be utilized to melt the PCM, which is in the annulus region of this experimental prototype. And the total energy or the capacity of this latent heat energy storage system, which we prepared, was 600 kilojoule. Of course, we have to maintain minimum heat loss. So for that, we try to utilize some sort of calculation for the heat losses, which was happening through the to the external environment through the pipe, and it was calculated to have a heat loss of around 4 to 7% in the range of temperature in which this experimental prototype was functioning. Now, if we are measuring the temperature, then it should be measured at certain locations so that we can validate it with the initial experiments which has been done by someone else. So for that, this slide shows the location of the various T-type thermocouple which has been used, and then to measure it and T-type thermocouples, and to measure it and compare it with the experimental verification which has been done by someone else, and also the numerical simulation which we have carried out for our present study. Now this graph reflects that we have a very good agreement with an error of around 6% and a coefficient of correlation of around 0.98. for the numerical analysis which we have done and comparing it with the experimental estimation which we are doing for this particular latent heat thermal energy storage. Now, we wanted to go for much more details to find at the exact location which we are being depicted by the literature. And then in that case also our root mean square deviation was not more than 6% for the various locations which has been depicted by previous literature, like Aggun et al. Has done one study. So we compared it with that and we found RMS deviation not more than 6% for the two locations which has been given by them. Now coming to this summary of the first part, of course, we have done the thermal characterization or estimation of the heat storage capacity of that particular phase change material. We found that there is a difference in the onset and the peak temperature for both the melting and the solidification. And of course, the specific heat is also evaluated for different temperatures. We designed an experimental prototype to find the efficacy of that experimental prototype, to find how efficiently it can be utilized to maintain the temperature at the required level when it is being utilized, or when it is being means sent to the field for doing this particular job of storing energy and utilizing it during the off peak time. Of course, we have developed a CFD model, which we will be showing in the next slide. And we have validated the model with the experimental work, which is cited in the literature, as I have already shown. Now coming to the heat transfer enhancement, which is very important for this latent heat energy storage system, is that we are utilizing both graphene nanoplatelets, which are introducing a kind of artificial thermal conductivity enhancement. And of course, we are going with the change in the shape of the system by introducing some sort of extended surface. Now, what is the novelty of this part? Of course, again, as I told, that there are not much studies being carried out by this finned latent heat energy storage system with GNP for the medium temperature application. For us, it is around 140 to 160 degrees centigrade. Then individual effect of incorporating fins, GNP, and a combined effect of both has also not been studied for this particular range of temperature for finned latent heat energy storage system. Now, fin height is to be one of the critical factors when we are planning to design a system with fins. Then of course we have to find out an optimum fin height which will not suppress the natural convection, and at the same time it will not act as a heat source. And this all studies have been done by taking the heat transfer model, including or incorporating the natural convection, and which are analyzed by utilizing the actual plant data for a double effect solar absorption system. Now, this is the schematic of the latent heat thermal energy storage system. You can see that we are having the first system shows that the annulus with the phase change material into it, and the second system shows the annulus with certain fins over it, and this is the geometry you can see. And of course, this phase change material will be just a bare phase change material, or it will be a mixture of phase change material and the graphene nanoplates. Just a second. Yeah. So when we are using this fins in the phase change material based annulus, then of course this increases the melting rate of the phase change material. And when we increase the height of the fin, this heat transfer due to convection reduces and the conduction only prevails. Therefore, there should be an optimum height which should be taken care of, and that optimum height was in the range of 50% of the annular space to 75%, at which convection current moves smoothly and can be utilized for transfer of heat. Now, this enhanced charging rate can be also studied in conjunction with the dual benefit of introducing graphene nanoplatelets with the fins. And we found that when we are introducing graphene nanoplatelets with the fin, then of course the melt front which is developed on the heated wall moves from top to bottom. But if we are utilizing graphene nanoplates and fins, we found that generally fins after a certain height, as I showed in my previous slide, like say 50%, and at 75% the convection reduces, this fins start acting as an individual heat source, which is a not very good situation. So we should find out what should be the optimum height of the fin. So this slide shows the various combination of the graphene nanoplates and the fins, where you can see that we are having a base case where we are not having any graphene nanoplates and fins. It is only the pure phase change material. Then we are having graphene nanoplates and we are having fins, and then we are having combination of all of them. So if we are having a combination of fins and graphene nanoplates, we find that only 3% reduction in the melting time is observed when we are increasing the fin height from 50 to 75%. Now temperature drops exponentially with the fin height. Increased fin height requires more material, making the system bulkier. Now melting is reduced by 68% using the combined effect of, when we are having the combined effect of both fin and graphene nanoplatelets, then we can say that there is a reduced melting time which is quite beneficial for this type of system and can be useful for designing it. Now coming to the summary of this particular study, it is the individual effect of incorporating both the fins and the graphene nanoplatelets, and the combined effect of both at different volume fraction has been studied. Of course, we know that there is an optimum height of the fin which is to be obtained so that the natural convection current is not retarded or impeded. So that was also one of the observation which we found. There are various heat transfer models, including natural convections, which are analyzed using the actual plant data for this double effect solar absorption cycle. Now, fins definitely, when we are studying the combination of fins and the graphene nanoplatelets, then it is said that fins outperform the nanocomposite system. And if we are increasing the volume fraction of graphene nanoplatelets, then it hampers the natural convection process, especially for larger annular space containers. So it is recommended that fin with small height, say 50% of the annulus, should be placed widely to avoid any hindrance to the convective current of the molten fission. This is a very interesting study where we are trying to find out, is there any effect on the shape of the phase change material based latent heat energy storage system. Now, when we are speaking about the shape factor, then in that case, generally we are using some sort of, you can say some sort of cylindrical type of shape when we are designing any latent heat energy storage system. Hello? Hello? Okay. Hello, can you hear me? That's what my question was. Hello, I think you are able to hear me. Okay.
Yes, yes, sir.
Okay, good. Thank you. So, study of an efficient latent heat energy storage system with a combination of fins and graphene nanoplates encapsulated in a conical shaped design is something which we will be looking at now. The charging performance of a finned conical thermal energy storage system encapsulated with nano enhanced phase change material is studied in conjunction to that of its cylindrical counterpart to find out what is the best geometrical design of the storage system that can be utilized for advantageously utilizing natural convection as the heat transfer. Is there any heat transfer enhancement technique which are to be utilized individually, or we can just go for this type of shape factor? Is it required to combine this with a highly efficient thermal energy storage system when we are saying to enhance the heat transfer technique by introducing graphene nanoplates or by introducing some sort of fins? So these are some of the features which we will be studying for this particular type of conical thermal energy storage system. And then we will see, is there any need to integrate this lab scale type of thermal energy storage, lab scale type of thermal energy storage system on the basis of the thermophysical properties evaluation at system level. Now, coming to this finned conical structure, you can see that this is the lab scale finned conical energy storage system which has been developed. And then we try to find out how better it is in comparison to that of its cylindrical counterpart. Both conical latent heat energy storage system with graphene nanoplates, with fins, and in combination of fins and graphene nanoplates have been studied, and then we try to find out which one is a better combination. Now this slide shows the numerical study which has been carried out for this finned conical latent heat energy storage system. So you can see that when we are having a conical type of latent heat energy storage system in comparison to that of the cylindrical one, the fins inside the PCM actually means act as an individual heat source and diffuse heat quickly. Now, conical latent heat energy storage system, it reduces the melting point by about 16%. Now, conical design utilizes natural convection more effectively as compared to that of its cylindrical counterpart. There is a factor which is known as the melt enhancement ratio. It is the difference between the liquid fraction of a particular system, whether it is a conical type of energy storage system, which is having fins incorporated in it, or which is having graphene nanoplates incorporated in it, or a combination of both. So the liquid fraction of that particular case is compared with the liquid fraction of the base case, which is neither having any fins in it nor having any graphene nanoplatelets into it. It is just a bare PCM. And then we try to find out what is the melting enhancement ratio of that particular system. Of course, in the case when we are having this type of graphene nanoplate based finned conical system, it reflects that there is an improvement in the total melting point in comparison to that of the cylindrical arrangement. However, it can be seen that the enhancement ratio for the finned conical latent heat storage system with graphene nanoplates is quite high. It is around 45%. But when we are speaking about a graphene nanoplate based latent heat energy storage system, which is having a conical shape, then it is having a negative ratio. So it is not a very good thing to explore. So conical shape actually counteracts the adverse effect of adding graphene nanoplates by improving the convective heat transfer coefficient. So that is a very important conclusion. This is the summary of this part of the this is the summary of this part of the system, where we are saying that conical based latent heat energy storage system, they can make use of natural convection advantageously by packing more PCM into the region and having a net reduction of 16% when it comes to the melting time in comparison to that of its cylindrical counterpart. Now, employing fins in the conical based latent heat energy storage system provide better heat transfer enhancement than the nanoparticles dispersion. Now, finned thermal energy storage system with 1% GNP, they does not show any substantial improvement in the thermal performance due to enhanced viscosity and restriction of natural convection. Of course, you can see that there is a negative ratio for 1% GNP. Now, coming to another study where we are planning to design a thermal energy based storage system where we can be utilizing two phase change material, two latent heat based material, which can be working in tandem with each other, placing them in the or we can place them either in a radial direction, or we can place them axially one after the other. So this type of systems are known as cascade latent heat storage system. One very important factor which should be kept in mind when we are utilizing this latent heat based thermal energy storage system is the testing of the heating or testing of the cooling for which this particular system has to work. So definitely heating rate or heating ramp of that particular system is quite important. At what rate you are heating the system, whether it is at certain degree centigrade per minute, like here we have taken 1, 5 and 10, because the results will be actually different for different heating rates. So we should find out what is the adequate heating rate which can actually help us to find out the better way of understanding the performance of that thermal energy storage system. So for this we have taken two type of phase change material. One is the HDP, that is high density polyethylene, and another one is the carnauba wax. So we have introduced both of them one after the other, either in the axial direction or in the radial direction, to find out how they can be effective to design a particular thermal energy storage system which can be efficiently utilized for giving the adequate energy storage for the cooling system which we are designing. So there are two types of system. One is the radial type and another one is the longitudinal type, or you can say axial type. Like along the axis we put the two PCMs and one along the circumference. And the phase change material which we have utilized is HDPE and carnauba wax. Now we have studied 5 different cases, where the first one is the one where we are only having a single phase change material, which is high density polyethylene, and then two different longitudinal and two different radial combination of carnauba wax and HDPE, where we are again having a decreasing order of melting point, an increasing order of melting point when it is being placed axially in the longitudinal direction. And then to find out whether HDP should be placed adjacent to the heat transfer fluid, or it should be the wax which should be placed adjacent to the heat transfer fluid. Of course, we then compared it with the base case where we are having only a single PCM, and that PCM was the high density polyethylene. And we found that for means there is a percentage increase in the means there is a percentage increase in the melting reduction in the melting time, and that can be compared with the base case, which is having a 6900 seconds as the melting time. So if we are utilizing various combinations, you can see that when we are comparing it with one longitudinal HDP type of situation, which is being utilized from a decreasing order of melting point. So when we are comparing it with that, then radial combination is having a percentage increase in the melting time, means betterment on the melting time. For this case of case 3, where high density polyethylene is adjacent to the heat transfer fluid. Of course, when we are comparing it with a single system, like when we are having a single PCM with a cascaded system, we can see that there is a 31% improve in the 31% improvement in the system in terms of its melting time when we are comparing it with the base system. This slide shows the temperature variation in the cascade system for latent heat thermal energy storage system. So the temperature versus time for various types of various locations of this cascaded system, where we are having HDPE and the Carnauba wax, which are being placed one after another axially, they are being studied. Now coming to the conclusions for this part, cascaded system of course performed better than the single type of phase change material. Total time for melting for the cascaded latent heat storage system is around 5000 seconds, and that of the single PCM system, when we compared, it is around 6800 seconds. So there is around 31% reduction in the melting time of the cascaded system when we are comparing it with the single PCM. Now coming to the radial placement, we found that radial placement is not effective for cascaded system, and in comparison to that of the axial placement of the phase change material, due to increase in the melting time by 104%. So you can see that there is an increase in the melting time by 104% when we are comparing it with that of the base case. Now, the thermal performance of the latent heat energy storage system, it depends much strongly on the accuracy of choosing the ramp rate. Like as you remember that I have shown different ramp rates, 1 degree centigrade per minute, 5 degrees centigrade per minute, and 10 degrees centigrade per minute. So this ramp rate selection is quite important to find out the thermal performance of any latent heat energy storage system when we are trying to characterize it utilizing differential scanning calorimeter. And ramp rate must definitely match with the observed heating rate in a real life application of latent heat energy storage system. Now coming to the overall conclusions, so we can say that natural convection definitely suppresses due to GNP graphene nanoplate dispersion, but this graphene nanoplate dispersion, it increases the effective viscosity, which is responsible for this reduced natural convection. Now empirical equations for viscosity are therefore utilized to find out how this spherical graphene nanoplates, which are dispersed in the fluid, can be can be modeled for observing whether there is any sort of correlationship between the non-spherical particles of the graphene nanoplates, which is dispersed in the PCM, with the spherical graphene nanoplates particle, to find out any strong correlation between them. Now, exceeding the graphene nanoplates further, definitely it will increase the viscosity, and thus the natural convection gets hampered. And in that way, the process especially will be more means I will say destructive. It will be more unfavorable when we are utilizing it for large annulus space containers. Now, when we found the empirical correlations, for estimating the viscosity of this graphene nanoplates, the correlations actually underestimated the overall viscosity of the nanoparticles. When we are speaking about the heat transfer enhancement through the fins and graphene nanoplates, now comparison between this latent heat energy storage system with the graphene nanoplates and nanocomposite system without fins, it actually reflects that fin system obviously outperformed the nanocomposite system. And of course, if you are saying that fin system outperforms the nanocomposite system, then it is good because a nanocomposite system in terms of techno-economics will also be more expensive as compared to that of the fin system. Now it is also concluded that the fins with smaller heights, like less than 50%, should be around 50% should be placed widely to avoid any hindrance to the convective current of the molten phase change material. Now coming to the latent heat storage system with 5% GNP, it shows a maximum reduction of 68% in the total melting time when it is compared with that of a storage system without fin. Now reducing the Stephen number, I think you know what is Stephen number. It is the ratio of the heat storage capacity to that of the sensible heat storage capacity to that of the latent heat storage capacity. So reducing the Stephen number and increasing the Reynolds number will of the heat transfer fluid, it enhances the rate of solidification. But of course, the reduction in the inlet temperature of the heat transfer fluid based on this Stephen number is more prominent than the mass flow rate for the thermal performance enhancement of this thermal energy storage system. Now coming to the effect of natural convection, of course, effect of natural convection is more predominant in the initial stages of solidification. And when we are going for the last stages of solidification, it is purely governed by conduction. And as I told that when we are having the fins, it can actually act as the heat source. So that is also one of the important conclusions. So heat transfer enhancement, when we are speaking about the conically shaped thermal energy storage system, that makes efficiently the utilization of the natural convection advantageously by packing more PCM quantity inside the upper region. And that way, the natural convection will be more predominant and will help us to get a better melting with reduced time. Now, employing PCM in this conical shape latent heat energy storage system is that it provides a better heat transfer enhancement than the nanoparticles dispersion. Earlier onset of Bernard convection cells, I think you understand what is Rayleigh Bernard convection. So earlier onset of Bernard convection cells in this type of conically shaped latent heat storage system has been very predominantly helpful for utilization of this natural convection advantageously as compared to that of a cylindrical type of system. Now, finned conical latent heat storage system with 1% GNP, it is having a negative enhancement ratio, if you remember. So does not show any substantial improvement in the thermal performance due to the enhanced viscosity. Now coming to the last one, the proposed design definitely reduces the melting time, which we have proposed over here by 57%, which is significantly enhancing the overall charging performance of the latent heat thermal energy storage system. Now the conical shaped latent heat thermal energy storage system shows better energy performance due to faster melting rate. Now coming to the performance evaluation of the last part, which is the cascaded type of energy storage system. Now cascaded system of course performs better than the single phase change material. Total time of melting for cascade latent heat energy storage system, it is reduced by 26% when it is compared with the single phase storage system. Now melting of Carnauba wax is faster than that of the HDPE due to high temperature differential between the phase change material, transition temperature, and the heat transfer fluid. Radial placement of the PCM is not effective for cascaded latent heat storage system as it increases the melting time by 96%. If you remember, I think let me go to that slide. So you can see that when we were having this radial type of arrangement where high density polyethylene is adjacent to the heat transfer fluid, then it is not a very, it increases the melting time by 104% in comparison to that of the axial type of system, in comparison to that of axial type of system. So that is something which is increases the melting time by 96%. Now the ramp rate is also quite important when we are doing that characterization of the phase change material, and it should be observed that the heating rate in a real life application of latent heat energy storage system should be compared with the ramp rate or heating ramp rate of that particular phase change material, so that we can properly judge the thermal performance of the latent heat storage system, and which strongly depends upon the accuracy of choosing heating ramp rates in DSC. So increase in temperature, inlet temperature, also reduces the total melting point. These are the journal publications which we got from this one. These are the references. So thank you. So I think I will take some 5 minutes break and then show you some slides on the characterization of this nano enhanced phase change material. Is it fine? Hello?
Yes, sir. Yes, sir.
Okay. So I will just take 5 minutes break and then again I will start. Thank you.
Okay, sir.
Okay, sir. పీపీటీ అడుగుతున్నారా స్టూడెంట్స్? పీపీటీ అడుగుతున్నారు. పీపీటీ అంటే షేర్ చేయి. అక్కడ అడుగుతున్నారు చూడు, ఇక్కడ ప్లీజ్ పోస్ట్ టుడేస్ సెషన్ పీపీటీస్. ఇప్పుడు రికార్డింగ్ ఎంత స్టాప్ చేయాలన్నా? రికార్డింగ్ లేదు చేస్తున్నాం సార్. మనం రికార్డింగ్ ఏంటంటే ఊరికే సీరియల్ మనం పెట్టుకుంటాం సార్. ఫుల్ పెట్టేటప్పుడు స్క్రీన్ షాట్స్ పెట్టుకుంటాం. స్క్రీన్ షాట్స్ పెట్టేస్తాం. నా స్క్రీన్ షాట్ పెట్టుకునేది అట్లా పెట్టేస్తాం. ఇప్పుడు అది లైవ్ ఏమైపోయింది? ఇప్పుడు ఫీడ్బ్యాక్
Okay, now we can start the next one. Hello.
Sir, please continue, sir.
Okay. No, sometimes it is.
ఈ సెట్
అంటే యాడ్ హోస్ట్ పెట్టుకుంటారు.
కంప్యూటర్ ఉంటే కంప్యూటర్ యాక్చువల్లీ క్లౌడ్ కదా. ఇప్పుడు వెబ్సైట్స్ ఎట్లా అంటే ఎప్పటికప్పుడు వెబ్సైట్స్ దీంట్లో ఒకటి ఫామ్ అవుతుంది.
ఆయన కూడా వైఫై నడుపుతున్నాడు.
Yeah. So now, as I was speaking about the differential scanning calorimetry, the ramp rate, when we have to increase the temperature per minute or per unit time for a particular type of characterization of the phase change material. So this instrument is quite handy for that. This is known as differential scanning calorimeter. So this differential scanning calorimeter, it comes quite handy whenever we have to find out what is the heat storage capacity of that particular phase change material. So in our lab, we are having an instrument from TA. It is known as the Q2000 analyzer. So basically this Q2000 analyzer can be utilized for estimating the heat storage capacity of any material. For example, the phase change material which we are utilizing at by giving different ramp rates and to find out which one is the most adequate one. Okay. Now, how this differential scanning calorimeter works? This differential scanning calorimeter, basically it will be having two plates. One will be having the material which you have to characterize, which is also known as the sample sensor platform, and another one is a reference sensor platform which will be not having any material into it. Now you will be providing the same heat rate to both the materials, the reference plate and as well as the sample plate, and then you will be finding out how much amount of heat is required per unit time, that is the heat rate, to get what is the overall heat storage capacity of that particular phase change material. So basically when we are speaking about this phase change material, they act as energy storage or energy dissipating system. So basically when we can speak about the thermal electrical network of this thermal circuit, then this phase change material, they will be working as one for the sample and another one for the material for which you are having it as a reference, which does not have any phase change, which does not have any material into it. And then you provide the same value of Q to both of them. And ultimately, by utilizing this equation, there is, you can see that the energy balance is happening. This is the DSC, which is having two plates. One is the sample and another one is the material which is to be characterized. And then you find out what is the difference between the two temperatures, like the reference and the sample. Of course, the resistance of this circuit is being governed by the thermal resistance which this particular reference or the sample is giving. So in that way, you can have the heat balance. So basically means this is the principle on the basis of which we estimate the heat storage capacity of this particular phase change material. And then we know that how this DSC works. So principally there will be one part which will be the heat flow to that, it is known as the principal DSC heat flow. And then there will be the capacity imbalance, which is being governed by the phase change material property of storing or discharging the heat. The means the way this phase change material will be storing the heat and it will be discharging the heat, on that basis only this heat capacity imbalance factor will come into picture. And then on the basis of this we find out how much amount of heat is being the same amount of heat, how much amount of temperature rise is there for the phase change material which is kept in the sample plate in comparison to that of the reference plate. And when we speak about any material, so basically in metallurgy, I think from your iron carbon equilibrium diagram, you will remember that there are various stages through which the material goes. So this phase change material also, as you are having the heat input, as you are increasing the heat by providing heat, and you are providing heat and increasing the temperature, so you will be seeing that over a period of temperature, there will be various phases through which this phase change material will be going. First one is the glass transition, second one is the crystallization. Before actual melting of that phase change material, which is in the solid state, it will be passing through this glass transition and crystallization. And once it reaches the melting stage, and then it goes further and forms the cross linking, and then further if you are going for heating, then it will be a kind of decomposition which happens. And similarly, when you have to solidify, again it has to go through this crystallization and then again come to this glass transition temperature. So basically I want to say that this is an entire cycle through which this PCM based material goes through when you are actually providing heat to that particular sample to find out what is the heat storage capacity or the specific heat of that particular material. Coming to the introduction of nanoparticles in the phase change material, you have seen that we have introduced graphene nanoplates with the phase change material to find out. Graphene nanoplates is always not a very good solution. Of course, it can increase the thermal conductivity, but when we are comparing it, when we are comparing the efficacy of that system with the fins, then it was not performing. So fins were outperforming. So now we will see how we can introduce this nanoparticles into the phase change material. So for that, we have actually in our lab prepared some high conducting titanium oxide nanoparticles inside our lab itself. So this is a process which is known as a continuous spray pyrolysis reactor, where we can utilize the titanium isopropoxide in the ethanol solvent, and we stir it for with the stirrer, mechanical stirrer, we stir it for 1 hour to make a clear solution, and then we spray it over the precursor to pass it on through this continuous spray pyrolysis reactor. And once it passes on this over the continuous spray pyrolysis reactor, at the end we collect the nanoparticles in a round bottom flask, which is being like a round bottom flask which is connected at the outlet. So we basically purge it into this collection chamber, which is one side introduced with titanium isopropoxide, and we get this titanium oxide nanoparticles on the other side. Now, how to mix this phase change material with this nanoparticles? So basically, this phase change material, as we know that here I have given a particular temperature. So at that particular temperature for our others application, means the temperature can be different. So on a hot plate, you mix that phase change material with toluene, and then what you do, you add the nanoparticles. For here example, if you are adding the titanium oxide nanoparticles, we can add it and then we can do the sonication. Once we do the sonication for nearly half an hour, and then again we stir it for nearly 1 hour, again by maintaining the temperature of the hot plate at certain temperature when it is liquid. Once it is liquid, and then we further heat it, because this is having toluene also, the toluene gets evaporated. Now it will be the mixed titanium oxide nanoparticles in the phase change material, which is then being dried in a vacuum oven. So this is the way how we construct this nano enhanced phase change material. So we have made a couple of different nanoparticles, and we have mixed it with our phase change material. So here we have taken anatase type of titanium oxide, and then we have taken rutile type of titanium oxide. This anatase type of titanium oxide, it is having more carbon content into it as compared to that of the rutile type of titanium oxide. And the phase change material which we have taken is nonadecane. So it is being utilized, first one where we are not having any impregnation of nanoparticles, one with the anatase type and another one with the rutile type, and another one where we are having only the phase change material. And then we found, after mixing it, after going through this particular process to get a nano enhanced phase change material, we found the effect of both specific heat and latent heat by introducing it to the differential scanning calorimeter, which I have already discussed at the beginning, and then find out what is the change in the phase temperature, what is the change in the supercooling effect, if any, if we are having this type of arrangement where we are having this nanoparticles being impregnated in the phase change material, does it have any effect on the supercooling temperature, and how the other phase change temperature is also getting affected when we are mixing it with them. Now these are the thermograms of the differential scanning calorimeter for just a ordinary phase change material and phase change material mixed with rutile type of nanoparticles, phase change material mixed with anatase type of nanoparticles. Of course, the heat storage capacity is one of the important criteria, as I told, and also the thermal conductivity. So these are various thermograms for the nano enhanced phase change material. This is the observation table, or you can see the results which we got. We found that although it was found that by introducing this nanoparticles, there is only a marginal impact on the latent heat storage capacity, but there is an increase of thermal conductivity by 37%. But again, we want a balance between the thermal conductivity as well as the heat storage capacity. But for the heat storage capacity, it was not having a huge impact. Only the thermal conductivity got increased by 37%. Now, for a particular application, it was actually for a building application where we were trying to utilize this nano-based phase change material into building the bricks. This type of situation was not very favorable, because we want a very good heat storage capacity also in conjunction with the enhancement of the thermal conductivity. So that was not a very appealing thing which we found by this introduction of nano enhanced phase change material. So I think with this I end my talk. So I can take questions from you all now. Yes. Is there any questions? Yes. Hello, Dr. Reddy.
Hello, please continue, sir.
No, I finished my talk. So are there any questions?
Okay. So dear participants, please ask any questions regarding this. So all of you, please unmute yourself and ask the doubts. So dear participants, you are requested to ask the doubts if you have any. Participants,
I think let me check the chat box. No questions, I think. Nothing is here. So I think they don't have any questions, Dr. Reddy.
so dear participants, please ask if you have any doubts. So Dibakar sir is waiting. So sir is asking flame or nano epoxy material. Sir, are you here?
Yeah, yeah.
Some participant is asking inflammable in flame nanomaterial.
I will check the chat box just a second. Yeah. In inflammability
How
test.
to measure the DSC?
DSC, that's a good question. DSC does not measure the inflammability of any particle. DSC only give the thermograms. DSC only give the heat storage capacity. For conducting the flammability test, you have to do some other arrangement, other type of environment where you can see that when the actual phase change material catches fire. DSC only gives the heat storage capacity, it gives the thermogram, that's it, nothing else. Is it clear, Dr. Siva Sarvanan? Welcome, welcome. That's a good question though, yeah. Yeah, any more questions?
Any question?
Okay, give information regarding the XRD. Look, XRD, SCM, and then TEM. These are more on the physical or morphological structure of the phase change material. This work was based more on the thermal analysis.
No, I think better. Any questions from the participants?
I think they are putting it in the chat box, so I can reply to them, Dr. Reddy. Yeah.
Please type in the chat box if you have any doubts.
Network issue. Someone is saying they have a network issue. Dr. Siva Sarvanan. Okay. The difference between thermal stability and reliability of PCM. Okay, okay, good, very good question. Um, to find the reliability of the PCM, you have to make the PCM thermally stable for certain cycles, because the PCM will get heated and then again melted, heated, melted. So generally for 2000 cycles, if the PCM can withstand the properties, generally for about 2000 cycles, the PCM is able to retain the property. The PCM can be declared thermally. Is it clear? SEM can be done anytime. Basically, you can get comparison in the structural changes that I mentioned at the beginning, like
Still any questions from the participants, please?
They are
Type
actually
in the chat
typing
box.
it. They are putting it in the chat box.
Yeah, sir. That's fine.
Same part. Not. Yes. There are many books.
Hello.
Yeah.
Yes, I have one query.
Yeah.
Hello. Yeah, if I have to experiment DST testing of polymer metal.
Polymer metal.
Yeah, polymers.
Okay. Okay.
So, means to say, I want to ask that which will give good result, polymer or smart materials
No,
by
DSC.
the help of
DSC.
DSC.
DSC can do any material test of
Okay,
whether it is a smart material or polymer material. It doesn't
okay.
matter.
Thank you.
Yeah. So mechanical research work.
టైప్ చేసి క్వశ్చన్ ఆన్సర్ టైప్ చేసి అంటే కొందరికి ఇది సిగ్నల్ ప్రాబ్లం ఉంది కదా అని టైప్ చేస్తాను చాట్ బాక్స్. అంతా లాస్ట్ క్లోజింగ్ టైంలో ఎంటర్ అవుతున్నారు. క్లోజింగ్ టైంలో ఎంటర్ అవుతున్నారు అందరూ.
చెక్ చేస్తాను కదా ఈజీగా గూగుల్లో సెర్చ్ చేసాను. నువ్వు రాసిన క్వశ్చన్ గూగుల్లో రావద్దు. ఫస్ట్ బ్యాంక్ డీటెయిల్స్ చదువుతాను. బ్యాంక్ డీటెయిల్స్
మార్నింగ్ ఫీడ్బ్యాక్ ఇంకా అడుగుతున్నారు. మార్నింగ్ ఫీడ్బ్యాక్
పక్క కూర్చుంటే కాదు డాక్టర్ గ్రూప్ కూర్చుంటాలా అట్లా కూర్చోవాలా ఎవరు తాను కూర్చుంటే అట్లా కూర్చోండి.
So participants, those who are not asking the questions, please mute yourself.
లేస్తానా లేలేనా
So I think no questions from the participants, sir.
Okay, sir. Okay, Dr. Reddy.
No, nobody is chatting in the chat box. So we'll close the session, sir.
Okay.
So first of all, I must thank to Professor Dibakar Garu for accepting our invitation to the expert speaker and the 2-week faculty development program on renewable energy intervention in industry, domestic and commercial applications in the online mode. So to give the expert talk on heat transfer studies of latent heat storage systems, so an application oriented study for sustainable air conditioning in both active and passive mode. So actually when we see the feedback, sir, it is excellent feedback given by the participants regarding the topic. So we must be thankful to you. So I hope the participants maybe gained a lot of information. So by your experience, so I hope all the participants may be benefited from this session. So I once again thank you, sir, for sparing your valuable time with us in the 2-week faculty development program, sir. So thank you, sir. Thank you very much for being with us. Thank you, sir.
Okay, sir. Thank you. So I can leave now?
Yeah, sir. Please, you can leave, sir. So dear participants, so today's sessions are over. So we'll be meeting you again in the tomorrow's morning session by Dr. K. Srinivas Reddy Garu, Professor of Mechanical Engineering, IIT Madras. So with the topic Rural Integrated Renewable Energy Solutions. Thank you, one and all, for joining in the faculty development program and for making the success. Thank you, one and all.